This represents a neutral atom in electrical balance. Earlier, we saw how an outside force can break an electron away from an atom and start an electron chain reaction, an electric current flow. One way to provide that outside force is by use of a magnet. It was proved with iron filings that a magnet has magnetic lines of force which connect its poles. For simplicity, let's consider the effect of this magnetic field on a single electrically neutral atom. Now, we move the magnet so that the magnetic field strikes the atom, supplying energy which forces an electron to leave its atom and become a free electron. The result is a sort of electron chain reaction. In a substance such as a length of wire, electrons are normally moving in all directions. But when a magnetic field is passed through the wire, several electrons are forced from their atoms and move in one direction. Now, in studying electricity, we're mainly interested in the movement of free electrons. So, for convenience, we'll look only at the action of electrons in the wire. When the magnetic field sweeps down across the wire, electrons move in one direction. When the magnetic field sweeps up across the wire, the electrons move in the opposite direction. This movement of electrons in either direction constitutes an electric current flow. If we move the magnetic field more slowly across the wire, fewer electrons are affected in a given period of time, and the electric current flow is decreased. And when we stop moving the magnetic field, the electric current flow stops, and the electrons again move in all directions. If this wire is connected to a meter, we find there is no electric current flow. When the magnetic field is moved down, this meter shows current flow in one direction. If the magnetic field is moved up, the meter shows current flow in the opposite direction. We can change the amount of electric current flow in several ways. Move the magnet faster, more current flows. Use a stronger magnetic field, still more current flows. Now coil the wire so that several turns are in the path of the field. Again, the current flow is increased. Stop moving the magnet, current flow stops.
This arc is being created by two charged bodies. One is a positive charge, the other a negative charge. In this case, the force is great enough to cause electrons to leave the negative charge, travel through air, which is an insulator, to the positive charge. We've also found that a battery has two charged materials. If a connection is made between them, electrons will leave the negative charge and travel to the positive charge. Well, let me make such a connection. And you see the results. Though the pressure is small, it caused enough electrons to flow to burn the wire up. Now, this force is called an electromotive force, or an EMF. It's electromotive because it motivates electrons to move. Now, other terms used to identify the force is electrical pressure, difference of potential, but you'll probably see this one used most often, voltage. Now, regardless of the term used to identify the force, the unit of measure is identified as volts. Now, I'm sure you've heard the expression, a 6-volt battery or 110-volt outlet. Well, in this discussion, we're going to see some of the common ways of producing an EMF, or voltage. Keep in mind that the basic requirement is to develop two charges, one positive, the other negative. Now, one method of developing a voltage is by chemical action. I'm going to build a chemical source by using a piece of zinc, carbon, and sal ammoniac powder, a chemical made up of chlorine and ammonia. Now, I'll mix water in the sal ammoniac so that it's in a paste form. Now, by mixing water in, it should activate the chemical, make it more active. Mix it up real good. Now I'll put in the zinc here and the carbon here. Now, here's what will take place. The sal ammoniac will react with the two materials and cause the zinc to gain electrons, the carbon to lose electrons. The zinc then will become negative, the carbon positive. Now, an EMF or voltage will exist between the two. Now, to check the results, I'm going to use this meter. Now, if a voltage or EMF does exist, it'll force electrons through this meter, causing it to deflect. So let's connect the meter to the material. One side here to the zinc, the other side here to the carbon. And of course you can see that the meter does deflect. Well, actually this is a crude form of dry cell battery. The two rods are called electrodes or terminals. The chemical is called an electrolyte. Well, a flashlight battery is an example of producing a voltage by chemical means. Now, by taking a look at a cutaway view, we can see essentially the same elements as the battery I just built. Now, the center post is a carbon rod. It develops the positive charge. The battery case is zinc. It develops the negative charge. The electrolyte is basically sal ammoniac powder, and it's packed between the carbon and the zinc. Now, this type battery develops an EMF or a voltage of about 1.6 volts. Here's another example of developing a voltage by chemical means. Its makeup is about the same as the flashlight battery. Taking a look at it, we see a carbon rod in the center, a zinc case, and a sal ammoniac electrolyte. Now, this battery also supplies 1.6 volts. In other words, the carbon-zinc combination generates 1.6 volts.
To oscillate is to swing to and fro, or vary from maximum to minimum. This pendulum, then, is a mechanical oscillator, and its purpose is to help the clock keep accurate time. We have arranged a mechanical oscillator to explain a few basic principles and to demonstrate its relationship to the electronic oscillator. With this device, we can graphically illustrate the action of an oscillator. This felt pen is suspended by two rubber bands, one on the top and one on the bottom, and will act as our oscillator. We'll supply the initial energy by stretching one of the rubber bands, and when it is released, it bounces back to normal. However, the velocity given the weight, the felt pen in its holder, causes the bottom rubber band to stretch a little bit, which will pull the pen back down past center, causing the upper rubber band to stretch again. Or energy is passed back and forth from one rubber band to the other. And this action continues until it finally comes to rest. We've arranged this device on a track so that it will bounce or oscillate up and down. And we have a motor that will cause the paper to move past the pen as it marks the path of the bouncing. In short, this device will record the action of the mechanical oscillator. Now, with the oscillator at rest and we start the motor, The marker draws a straight line, our zero reference line. We add energy, and our oscillator will bounce up and down. The felt pen marking on the paper, drawing a waveform as it plots the action of the graph. Now notice the similarity to an AC sine wave. We can also see that the amplitude of the oscillations steadily decreases from the point where energy was initially supplied. What causes this damping action? What causes the decrease in amplitude? Well, in this case, the action of the oscillator is gradually diminished by the friction of the slide, the friction of the pen on the paper, the force of gravity acting on the weight, and the resistance of the rubber bands themselves. In short, the diminished amplitude on the graph is caused by inherent resistance in the oscillator. Now, only if we overcome this resistance can we make the device oscillate continuously. And since this is a rather crude device, it has a large amount of resistance. We must add large amounts of energy to overcome the built-in opposition. Let me add a little more ink to the felt pen, and we'll see if we can demonstrate this. Start the paper going past the marker. We continually add energy, and if we could add it in the proper amount, we would have a waveform of constant amplitude and constant frequency. Now, our graph shows us that this method produces a waveform of almost continuous amplitude and stable frequency. This is essentially the wave shape we want out of the LC oscillator. Constant amplitude and constant frequency. Of course, this graph does not show that by any means, but it does illustrate the point. All right, let's compare the two. The rubber bands and the weight determine the frequency of the bounce. Resistance causes the amplitude of the bounce to gradually decrease. But if we feed energy to the device, it will bounce continuously. In the LC circuit, L and C compare to the rubber bands and the weight, the frequency determining device. And as you recall, the resonant frequency of the tank can be determined by the formula F sub O is equal to 0.159 over the square root of LC. Or very simply, the frequency is determined by the size of L and C. Now, to be sure you understand how this circuit will oscillate, let's follow the action step by step. First, we'll need a power supply to provide the initial energy. In this case, a battery. This switch will allow the capacitor to be connected to the battery or to the coil. If we flip the switch to A, the capacitor charges to the battery voltage. Move the switch to B, and the capacitor is disconnected from the power supply, though it is still fully charged. When the switch is moved to C, the capacitor will start to discharge through the coil, causing current to flow in this direction. Now, as you know, when current flows through a coil, the field about the coil expands as current increases. So as long as current increases, the field continues to expand. At the point when the charge on the capacitor is almost depleted, the amount of current begins to decrease. At the instant current begins to decrease, the coil will oppose this change. That is, the field will begin to collapse, reversing direction, thus reversing the polarity of the induced voltage, causing current to flow in the same direction. Or the coil becomes the source as the energy stored in the magnetic field is put back into the circuit, causing the capacitor to charge in the opposite direction. Now, when the field about the coil is completely collapsed, current is zero, and the capacitor is charged in the opposite direction. And it will again discharge through the coil. As current begins to increase, the field about the coil expands. Now notice that current is flowing in the opposite direction. So we'll show this on our graph. At some point, current will begin to decrease. And when it does, the magnetic field will start to collapse, reversing direction and returning energy to the circuit, which will cause the capacitor to recharge in the original direction. Now, when the coil's field is completely collapsed, current is zero and the capacitor is charged. Notice that the current on this alternation was not quite as great as the original alternation due to the circuit resistance, which we have not shown in this simplified drawing. Thus, as this oscillating action continues, the output waveform will continually decrease until the energy in the circuit is completely absorbed. The current waveform generated by the LC circuit looks very much like the graph of our mechanical oscillator. Why did the amplitude of the oscillations decrease? In the mechanical oscillator, inherent resistance or friction. Now, if we apply this reasoning to the LC circuit, it's obvious that the decrease in amplitude is caused by internal circuit resistance. That is, the resistance of the wire finally dissipates all of the energy. Now, we'll represent this resistance here. The amount of internal resistance will determine the quality of the circuit. And you should recall that the Q of a coil is equal to X of L over R. Thus, the higher the Q, the longer the circuit will oscillate because there's less energy dissipated in the circuit. But even the highest quality components offer some resistance. So to generate a waveform of constant amplitude, energy must be added to the circuit at the same rate that it's being lost, in much the same way that we fed energy to the mechanical oscillator. The ringing action of the LC circuit is often referred to as the flywheel effect, because like a flywheel, once it's started, a small amount of energy added at the right time and in the right direction will keep it going. And also like the flywheel, if energy is added in the wrong direction, the flywheel will stop. So energy must be added at the right time in the LC circuit. For example, if a positive voltage were applied at time 2, the energy lost in the first cycle would be replaced and the amplitude brought up to the desired value. If energy were added every cycle, we could maintain constant amplitude. However, if this positive voltage were added at time 1, it would cancel the energy in the circuit and the circuit would stop oscillating. Thus, like the flywheel, the energy fed to the LC circuit must be of the proper amount to overcome the resistive losses in the circuit, and it must be delivered at the right time, or in phase with the oscillating signal. Now, the way this is usually accomplished is through an amplifier. The frequency determining device provides an input to the amplifier. The amplifier must provide enough gain so that part of the output can be fed back to the input LC circuit to sustain oscillations, and of course, provide enough signal for an output. Now, the energy must be fed back in phase or regenerative. Now, because many amplifiers shift the phase of the signal by 180 degrees, there may be phase shifting networks required in the feedback path. Various methods are used: RC, LC, RCL, or transformers between the output and the input. Now, which system is used will be determined by the type of oscillator circuit and its application. The important thing is that the energy fed back be in phase with the signal generated by the frequency determining device. This demonstration will convince you that feedback does occur and will cause a circuit to oscillate. The microphone here is connected to the input of the audio amplifier. The speaker is connected to the output. Between the two, I have a piece of acoustical tile. If I remove the tile and allow the microphone to pick up some of the output sounds, the amplifier will go into oscillation. Now, even though this circuit is not designed as an oscillator, if we feed the output to the input or develop feedback, it will oscillate. And if you've ever tried to listen to a PA system that has been plagued with feedback, you'll agree that in this case it is undesired. But before we go into what is happening in the amplifier, let's be sure we understand why it oscillates. Any sound picked up by the microphone is fed through the amplifier and out the speaker as sound. If the microphone picks up the sound coming out of the speaker, the output is feeding the input and the stage oscillates. Now, since there's no way to control the amount of feedback, the strength of the oscillator signal continues to increase. You can hear this increase when we remove the tiles slowly and allow the microphone to pick up the speaker's output. The squeal builds from a relatively low level to a very high level. And if allowed to continue, very high oscillating currents are built up that may damage circuit components. For this reason, the amount of feedback must be controlled in an oscillator. The correct amount is just enough to overcome the losses in the circuit. Any amplifier will oscillate if feedback occurs. But what is the frequency of oscillation? In the LC circuit, we found that frequency is determined by L and C in the tank. Now, the same thing is true in the amplifier that oscillates. But since there is no frequency determining device, the frequency of oscillations is determined by distributed L and C. That is, the input capacitance of the amplifier, the inductance of the leads, or any inductors and capacitors in the circuit. Very difficult to predict the frequency. And thus we see the need for a frequency determining device. In this case, the LC combination. These component values are carefully calculated to oscillate at exactly the right frequency. Then the exact amount of feedback. And we have an LC oscillator that provides a signal of constant frequency and amplitude. One other factor should be considered, and that is loading the oscillator circuit. We can see this effect clearly by looking again at our basic circuit. We've already pointed out that the feedback overcomes the loss caused by the internal resistance of the circuit, which is small when a high Q tank is used. However, there is another quality factor that concerns external circuit resistance, and in this case, the resistance should be high. In other words, the amplifier connected to the frequency determining device should offer maximum impedance to the tank. Even then, there'll be some energy loss to the external load, which must be regained by increasing the feedback. Now, because loading and power surges can cause shifts in amplitude and frequency, the oscillator stage is usually isolated from the rest of the equipment by special amplifiers or other circuits. Now, the exact kind of isolation depends on the particular application or use of the oscillator. However, there are several basic oscillator characteristics that are always true, whatever the type or application. First, any oscillator should develop a stable frequency and a signal of constant amplitude. Now, be sure you understand that this statement applies to all oscillators, the LC or any sine wave oscillator, as well as the sawtooth, square, rectangular, or trapezoidal oscillators. all of them, should generate constant amplitude and frequency. Now here's a list of the basic requirements that also applies to all oscillators. First, of course, a DC power supply. It may be a simple battery or a very complex, carefully regulated circuit. Next, a frequency determining device. We have seen that an amplifier will oscillate without a frequency determining device. But the frequency is determined by distributed L&C, which makes frequency difficult to calculate and erratic. This kind of oscillation is usually undesirable. A frequency determining device, in this case the LC tank, provides a stable, easily calculated frequency. Feedback is required to sustain oscillations in the frequency determining device and is usually accomplished with an amplifier. The frequency determining device provides an input to the amplifier, and the amplifier must provide enough gain so that part of the output signal can be fed back to overcome resistance in the tank and replace any energy lost through loading. Of course, the feedback must be regenerative or in phase. Thus, a phase shifting network between the output and the input may be required. There may be other requirements depending on the application of the oscillator, which you'll discover when you study a particular piece of equipment. But the main idea is that all oscillators are basically the same. So whatever the type or the name of the circuit, all oscillators will require a power supply, a frequency determining device, feedback, usually from an amplifier. Now, if you apply these basic principles, oscillators will be much easier to understand. Just like this clock, the spring drives the gears that feed energy to the pendulum, which is the frequency determining device. And thus, the pendulum moves at a constant frequency and amplitude, which, of course, is the purpose of any oscillator.
We've seen that using an insulator, in this case air, to carry current is impractical because very high and dangerous voltage is required. On the other hand, when a good conductor is used, too much current flows and destroys the conductor. We require a happy medium, a material that will allow enough current to flow to do the job without burning up the conductor. And at the same time, of course, using a low, safe voltage. Let's look at this again. Connecting this wire across the battery, it doesn't burn up. It starts to heat up until it's red hot, but it doesn't allow too much current to flow. The reason that it doesn't burn up is because this is a semiconductor material. It offers resistance to current flow, opposition to the movement of electrons. By introducing resistance into the circuit, then current can be controlled. In this lesson, we'll discuss the factors that determine resistance, and we'll talk about resistors, devices that are designed to offer specific amounts of resistance. Now, we've seen the effects of resistance many times in previous lessons. For example, why didn't this light bulb burn up when we connected it across the battery? Well, it limits the current to the amount required to produce light. If it didn't limit current, it would burn up. So the bulb offers resistance to current flow. It's obvious then that we need resistance to control current. But why do some materials offer a lot of opposition and others very little? Basically, it's the atomic structure of the material. For example, we've said that conductors have many free electrons. They allow current to flow with ease. If conductors don't oppose current, then they must have very little resistance. Well, that's why the wire burned up earlier. It was a copper conductor. On the other hand, insulators have very few free electrons. In most cases, they prevent current flow. Insulators then have a high resistance. That's why a large voltage was required to move electrons through air. A low resistance here, a high resistance here. But what about these materials? Their characteristics are between conductors and insulators. Then using semiconductor materials, we can control current from a very small value to a very large value. Now, there are several factors that determine the resistance of semiconductor materials, but the primary one is the number of free electrons they contain. In other words, the material they're made of. So remember, the materials used to make up the semiconductor is the prime factor. There are some more. Let's look at them. These are length and diameter. Now, to show this, we'll use this bulb, these batteries, and 3 wires made of semiconductor material, nickel and chromium to be specific. Let's look at the wires. This one is very small in diameter. The next one is a little larger, while the third one is very large in diameter. Now, the wires are the same length. Before we begin, let's check the intensity of the bulb with just the resistance of the bulb opposing the current from the battery. As you can see, the bulb is lit very much, very bright. Now, in the first example, we'll use the small wire, and we'll see the factor length and how it affects resistance. Now, with the connection here and here, the battery must force current through the resistance of the bulb plus the resistance of this wire. There's very little current through the bulb. It's hardly glowing. Now, what I'm going to do, I'll slide this connection down the length of this semiconductor material. In other words, I'll decrease the length, and we'll see how it affects resistance. Okay, let's watch it. Very little current there. Decreasing the length, notice that the bulb starts to glow more and more. Now, let's stop right here. I've decreased length. I've increased the current. So the resistance must have decreased. There's more current through the bulb. Well, let's go on down to the end of the wire. Watch the bulb. As I decrease length, I decrease resistance because the bulb is glowing more. Well, this is pretty obvious. Let's take a look at it. When I had the bulb over here, the electrons had to travel the full length of this resistance material. So it's only natural that it's going to encounter more opposition. But as I decreased the length, I decreased resistance, and the bulb glows brighter. Then length is definitely a factor that determines resistance. Now, in the next one, we're going to increase the diameter of the wire. Let's see what happens to resistance as we do this. Of course, with the small diameter wire, there's very little current through the bulb. Let's go to the next one. As I increase diameter, there's more current through the bulb. This means that resistance decreased. Let's go to the next one. Increased diameter, more current through the bulb. So resistance must have decreased. Now, let's make sure that we understand this. Let's do it again. With a small diameter wire, very little current, a large resistance. Increasing diameter, we decreased resistance. Increasing diameter again, decreased resistance. This is also easily understood. This in view of a large and small wire shows that the large wire contains more atoms. With more atoms, there are more electrons available. And with more electrons available, it will pass current easier than the small wire. Then as the diameter of the material increases, its resistance decreases. Now, the third factor that determines resistance is the temperature coefficient of the material. Temperature coefficient simply means the effect that temperature has on the resistance. To show the effect of temperature, we'll use a piece of tungsten. This filament from an ordinary light bulb is made of tungsten and will do the job very well. First, let me check the bulb to make sure that everything is all right. Okay, that's just the resistance of the bulb opposing current. Now I'll add the tungsten to the circuit. And you can see that it had a little bit of effect on current because it did decrease the intensity. But when it's cool, it has a small effect on resistance. Now, to apply heat to the material, I'll use a small torch, so let me light it and set the flame so that it's just about right. Now, watch the intensity of the bulb as I heat the tungsten. Applying heat to it, notice that the bulb goes out. The resistance of the tungsten has gone up, which reduced the current through the bulb. Now, when I take the heat away and the tungsten starts to cool off, its resistance goes down because there's now current through the bulb. Now, let's try it again to make sure you understand what I'm doing. As I apply heat to the tungsten, its resistance goes up, there's less current through the bulb. When I remove the heat, the tungsten cools, resistance goes down, current through the bulb increases. Now, if resistance goes up when the material gets hotter, as it did in this case, the material has a positive temperature coefficient. Tungsten then has a positive temperature coefficient. In the next example, let's use a piece of germanium. Now, I'm going to decrease the flame just a little bit. Let's try a piece of germanium, heat it, and see what happens. First, let me check out the circuit. Okay, there's the bulb without the germanium. Okay, now I'll add germanium to the circuit. Remember, the germanium is now opposing current. As you can see, the bulb is out, indicating that the resistance of the germanium is so large that it prevents current through the bulb. Now, watch what happens when I apply heat to the germanium. Its resistance must have gone down because the current through the bulb increased. Now, watch the bulb, though, as the germanium starts to cool off. As it cools, its resistance goes back up, stopping the current through the bulb again. Okay, let's try this one more time. Applying heat to the germanium, its resistance goes down, current through the bulb. But as the germanium cools off, its resistance increases and will stop current through the bulb. Now, materials that exhibit this property have a negative temperature coefficient. And I might add here that most materials will exhibit a positive temperature coefficient. Okay, length, diameter, and temperature coefficient are all factors that determine the resistance. Now, remember also, the materials, the combination of materials used to make up these resistive devices will determine resistance. Now, since different circuits will require various amounts of resistance, there's a requirement for measuring the amount of resistance. Well, resistance is measured in units called ohms, O-H-M, ohm. Now, here's what an ohm is. If there's 1 ohm in the circuit, let's say this is 1 ohm, 1 volt will cause 1 ampere of current. So remember, 1 ohm of resistance means that it will limit the current from a 1 volt source to 1 ampere. Now, the symbol for resistance is the capital letter R. And remember, it's measured in ohms. Now, to provide the various resistances needed in electronics, devices with specific ohmic values have been developed. These devices are called resistors, and basically they're semiconductor materials. Now, by semiconductor material, I mean that they are not a good conductor. They're not a good insulator. They exhibit characteristics between these two. Let's look then at some common resistor types. This one is a wire-wound fixed resistor with a variable sleeve here. Now, it's made of wire very similar to the wire that we used in the demonstration earlier. by moving this sleeve, we can change the length of the wire, say from this contact to this one, thereby changing the amount of resistance. Let me slide the sleeve. As I slide the sleeve down, I increase the length of the wire, which means that I have changed the resistance from this terminal to this one. So by moving this, we would have a variable resistor, wire wound. Another type of wire wound resistor has fixed taps. Now in this case, you would select different taps, thereby changing the length of the wire that you're using, changing the resistance. So in this case, you could have several different resistances from one resistor. Another common type of wire wound resistor is a variable wire wound resistor. Now, the wire is here in this semicircle, and it's a fixed resistance from this tap to this tap. The variable part of the resistor is provided by this contact. For example, if I move the contact to here, I've increased the length of the material that I'm using from the contact to this terminal. Therefore, I've changed the resistance. When I move the contact, I change the length of the wire, change resistance. So a variable wire wound resistor. Again, you can select several different values of resistances from one resistor. Another common type of variable resistor is this one. Now, it's made of a carbon compound. Now, it's very difficult to see the carbon compound, but it's down in here. It's a carbon disc. But again, by using this little contact right here, and by changing that contact, we change the length of the material being used, thereby changing resistance. A variable carbon resistor. Probably the most common resistor is this one, a fixed carbon resistor. Now I've cut it in half so that you can see the carbon compound inside. This carbon rod has a fixed resistance. It's made of carbon, materials such as rubber, talc, things like that. Probably the most common type of resistor used. The carbon fixed resistor. Okay, length, diameter, temperature coefficient, the combination of the materials used to make up these devices all determine resistance. Now, there are all types of resistors. They come in a variety of shapes, sizes, but they're all designed to do a specific job. One example is the volume control in this radio. It's a variable carbon resistor. As the shaft is rotated, resistance changes, which changes the volume.
Hello, Mrs. Mills, Atlanta?
Now, if we looked at some more equipment, we'd find a variety of other resistors. For example, here is a variable carbon resistor. It's used to change the voltage or the current, as the case may be. Looking on down, we'd find a variety of resistors. Resistors required to make tubes work, to make transistors work, all kind of resistors, a maze that are essential to the operation of the electronic components. Looks complicated, doesn't it? Well, it isn't complicated. In the next lesson, we'll start to solve this maze by discussing circuit components and their symbols. I'll see you then.
This toy train is powered by an electric motor housed inside its engine. The voltage required by the motor in order to operate is about 15 volts. When the power cord is connected to a standard 110-volt AC outlet, however, only the required 15 volts is applied to the electric motor. What is it that accounts for this reduction in voltage? This fluorescent light, too, requires a certain amount of voltage before it will operate. The voltage required in this case, though, is several hundred volts. Just like the train, however, when its power cord is connected to a 110-volt AC outlet, the required several hundred volts is applied to the light. What is it that accounts for this increase in voltage? The answer to both of the questions just posed for you, and also the subject of this lesson, is the transformer. Now, just what is a transformer? Well, basically, we can say it's a device that does just what its name implies. It changes or transforms voltage. If the transformer reduces the voltage, as in the case of the train, it's called a step-down transformer. Whereas if the transformer increases the voltage, as in the case of the fluorescent light, it's called a step-up transformer. The ability of the transformer to transform voltage can be understood best if we first examine an important phenomenon in electricity, the magnetic field. When electric current passes through a wire, an invisible band of magnetic force is set up around the wire. In the case of direct current, this magnetic field expands to a certain point and stays there, except, of course, it's traveling around the wire all the time. For instance, if you were to grasp the wire in your left hand and extend your thumb in the direction the current is traveling, the magnetic field will be circling the wire in the direction of your fingers. In alternating current, the magnetic field expands and contracts every time the current changes direction. And now here comes the payoff. This phenomenon gives a wire carrying alternating current the power to induce a voltage in a second wire placed beside it. How come? Well, the second wire will pick up voltage from the wire carrying the current because the magnetic field expanding and contracting through the second wire induces this new voltage. This is called electromagnetic induction, and it's the principle on which the transformer works. Remember, a magnetic field surrounds every live wire. Now, in order to concentrate the strength of this magnetic field, we coil the wire, thereby intensifying the magnetic attraction inside the coil many times over. The coil that carries the current is called the primary coil. Beside it, we place an additional coil called the secondary coil. Notice that the magnetic field from the primary coil travels across the gap to the secondary coil. We can increase the strength of this magnetic field even further if we place an iron core inside the two coils. Now all the magnetic field will travel inside the iron core because it offers less reluctance than the air around it. Now this in turn permits a greater amount of energy to be transferred from the primary to the secondary coil. This process of transferring electrical energy, or voltage we might say, from the primary coil to the secondary coil through electromagnetic induction is commonly referred to as transformer action. As we said before, the transformer can step a voltage up or it can step it down. The voltage increase or decrease is determined by the turns ratio of the particular transformer. The turns ratio is the ratio of the number of turns in the primary coil to the number of turns in the secondary coil. For example, if the primary coil has 500 turns and the secondary 1,000 turns, twice the number of the primary, or a ratio of 1 to 2, let's see what happens to the voltage. Presto, Mr. Volt became twice his size. The ratio is 1 to 2, so the voltage doubles. In this case, the voltage is stepped up because the secondary coil is the largest. If, on the other hand, the secondary is the smallest, the voltage is stepped down. Either way, however, voltage is transformed. Now, it's important to realize that a transformer doesn't add any energy to a circuit. It merely changes or transforms the energy that already exists in the circuit from one voltage level to another. The total amount of energy in the circuit must remain the same. Now, if it were possible to construct a perfect transformer, there would be no loss in power in the transformer. power would be transferred from one voltage current level to another. Since power is the product of current times voltage, an increase in voltage by means of the transformer must result in a decrease in current. And likewise, a decrease in voltage by the transformer must result in an increase in current. Now, stating in another way, we can say that a transformer which increases the voltage by a given ratio will decrease the current by the same ratio, and vice versa. For example, if we apply 10 volts at 10 amperes, or a power of 100 watts to the primary of a step-up transformer, which has a turns ratio of 1 to 10, the voltage in the secondary would be 10 times that of the primary, 100 volts. But the current in the secondary would be 1/10 that of the primary, 1 ampere. The power in the secondary, however, would still be 100 watts. Now let's suppose the same 10 volts at 10 amperes was applied to the primary of a step-down transformer, one which has a turns ratio of 10 to 1. The power in the primary would again be 100 watts. The voltage induced in the secondary would now be 1/10 that in the primary, 1 volt. The current in the secondary would now be 10 times that in the primary, 100 amperes. The power in the secondary, however, remains at 100 watts. Now, thus far, you've seen that if the secondary of a transformer has more turns than the primary, the voltage is stepped up. Whereas if the secondary has fewer turns, the voltage is stepped down. Now, later you'll see transformers in which the primary and secondary have the same number of turns. Such a transformer has a turns ratio of 1 to 1. Unlike the step-up and step-down transformer, a 1-to-1 transformer neither increases nor decreases voltage. The voltage and current available at its secondary is the same value as that applied to its primary. Now, the transformers we've dealt with thus far were assumed to be ideal transformers. That is, they were considered to be 100% efficient. Such an assumption is quite all right from a theoretical viewpoint. However, from a practical viewpoint, the construction of an ideal transformer is an impossibility. The primary reason for this can be realized by discussing a factor known as the coefficient of coupling. The coefficient of coupling, which is represented by the letter K, is a measure of the degree of coupling between the primary and secondary coils of a transformer. The coefficient is obtained by dividing the number of magnetic lines cutting the secondary coil by the number of magnetic lines actually produced by the primary coil. For example, if the primary of this transformer produced 10,000 magnetic lines, but only 8,000 lines cut the secondary, then the coefficient of coupling would be equal to 0.8. Now, if all of the magnetic lines produced by the primary coil of a transformer were to cut the secondary coil, the coefficient of coupling then would be 1. The coefficient of coupling for an ideal transformer is also 1. However, even with high permeability iron cores, a few of the magnetic lines fail to cut the secondary and are, in effect, lost. Now, this prevents the coefficient of coupling from ever being exactly unity, or 1, in an ideal, or I should say, in a practical transformer. It should be pointed out, however, that a coefficient of coupling of 0.98 is possible between the coils of a well-designed transformer. Now, in general, there are 4 types of transformers. They include power transformers, audio transformers, RF, radio frequency transformers, and finally, auto transformers. Power transformers are used to step up or step down AC voltages occurring at the power frequencies, which you'll recall include 50, 60, and 400 cycles per second. It should be pointed out, however, that a particular power transformer is designed to operate at only one of these frequencies. For example, a power transformer that's designed to operate at 60 cycles per second couldn't be operated at 50 and 400 cycles per second. Now, quite frequently, and especially when dealing with schematics, you'll have to recognize a type of transformer by its schematic symbol. The schematic symbol for the power transformer can usually be identified by there being more than one secondary winding. In this case, there are two secondaries. However, other power transformers may have a different number. You'll notice that each secondary has a different number of turns. One of the secondaries has fewer turns than the primary. Therefore, it produces less voltage than that applied to the primary. The other secondary, though, has more turns and thus produces more voltage. Now, you'll also notice that the power transformer is constructed with an iron core. Now, unlike a power transformer, which is designed to operate at a specific frequency, the audio transformer is designed to operate over the entire range of audio frequencies, which is generally considered to be from 20 to 20,000 cycles per second. The schematic symbol for the audio transformer resembles that of the power transformer. The audio transformer, however, usually has only one secondary winding. Like the power transformer, the audio transformer, too, is usually constructed with an iron core. Well, at frequencies above 20,000 cycles per second, the RF transformer comes into use. At these frequencies, hysteresis and eddy current losses in an iron core become so great they have to be prevented. Therefore, RF transformers generally have an air core. The schematic symbol for an RF transformer, then, is easily identified by there being no vertical lines between the primary and the secondary coils. Now, a special type of transformer which uses only one winding for both the primary and the secondary coils is the auto transformer. In addition, an auto transformer can be used either as a step-up or as a step-down transformer. When used as a step-up transformer, all of the primary winding is part of the secondary winding. Here you see that the winding has a total of 1,000 turns. 600 of these turns serve as the primary, while the entire 1,000 turns serve as the secondary. Now, when an auto transformer is used as a step-down transformer, all of the secondary winding is part of the primary winding. Here we see now that the entire 1,000 turns are serving as the primary, while only 600 are serving as the secondary. Now, auto transformers are sometimes constructed with a sliding contact, as we see here. When a control is varied on the transformer case, the secondary voltage can be varied from the maximum voltage induced in the winding down to 0 volts. As you can see, this type of transformer is called a variable auto transformer. However, it's probably most commonly known as a variac. Now, auto transformers are normally used in power circuits. However, they may be used for audio or RF use. That is, designed for audio or RF use. The symbol for an auto transformer used in a power or an audio circuit will indicate an iron core. The symbol for an auto transformer used in an RF circuit will be the same, except it will not indicate an iron core. Now, even though we showed you definite symbols for each of the types of transformers, you may find occasions when they'll differ. However, in these cases, you can readily tell the type of transformer simply by noticing where it's being used in the circuit. For example, if a power transformer is being used in a power supply, or if a transformer is being used in a power supply, then you can rest assured it's a power transformer. Now, earlier we showed you, or you learned, that the turns ratio of a transformer determines whether the voltage is stepped up or stepped down, and by what amount. There will be times when you're troubleshooting electronic equipment, however, that the turns ratio of a particular transformer won't be given. Thus, you'll have to determine whether the transformer is a step up or step-down transformer by other means. Now, one way to readily determine this is simply by applying voltage to the primary winding and then measuring the output voltage of the secondary winding. Now, over here, I have a transformer demonstrator. As you can see, it's composed of an iron core and two windings. One of these windings will serve as the primary of the transformer, while the other winding will serve as the secondary. In the demonstration, we'll be using the bottom winding here as the primary. Now, here I have a power supply, and from these two terminals on the power supply, we can obtain 6.3 volts AC. I'm going to apply that 6.3 volts to the primary of this transformer, and then we'll use our PSM6 and measure the voltage available at the secondary. Let's go ahead then and apply the 6.3 volts to the primary of the transformer, which, as I've already mentioned, is the bottom winding here. Now, if we'll turn the power switch on, we have 6.3 volts applied to the primary of the transformer. Now, the PSM6 has already been set up to measure AC voltage on the 50-volt range. So, let's go ahead then and see how much voltage is available at the secondary. If we'll take a look at the AC scale now, and it'll be the middle row of numbers, you can see it indicates 11 volts are available at the secondary. Now, since this is greater than the 6.3 volts applied to the primary, this then readily tells us that this transformer is a step-up transformer. Now, if the transformer in question was a step-down transformer, then it's obvious that just the opposite would be true. The voltage measured across the secondary would be less than the voltage applied to the primary. Now, another way you can determine whether a transformer is a step-up or a step-down transformer is by means of resistance readings. Since a transformer winding is a continuous piece of wire, it should have a definite amount of resistance. And the more turns the winding has, the greater the resistance will be. Therefore, by comparing the resistance readings of the various windings, we can determine the turns ratio of the transformer, and thus whether the transformer is one which steps the voltage up or steps it down. Well, let's measure the resistance of the windings in our transformer we're using here and see if this holds true. Before we do it, however, there's a few words of caution I should point out, and that is, whenever making resistance checks in a transformer, ensure there is no voltage applied to the transformer. So let's turn the voltage off, disconnect the lead so we'll get accurate readings on our transformer windings, and let's proceed with the checks. Now, first, we'll have to set the PSM6 up so it'll read resistance. We'll place the function switch in the ohms position, and we'll place the range switch in the ohms times 1 position, since we're dealing with a relatively small amount of resistance here. And now, so we'll get an accurate reading, let's zero the meter. Well, we can see it was already zeroed. So let's go ahead now and measure the resistance of the primary winding. All right, if we'll take a look at the meter now, we'll see that the primary winding has about 10 ohms of resistance. All right, let's go on over to the secondary winding and see how much resistance it has. Remember now, we're on the ohms times 1 scale, And this time we can see the PSM6 indicates about 20 ohms of resistance for the secondary. Now this indicates then that there's twice as many turns in the secondary as there is in the primary. So the turns ratio is 1 to 2. Thus the transformer is indeed a step-up transformer. And a step-up transformer then, the resistance of the secondary is higher than the resistance of the primary. So for a step-down transformer, just the opposite would be true. The resistance of the primary is higher than the resistance of the secondary. Now, two other checks you'll have to perform on transformers quite frequently are those for an open or a shorted winding. Both of these checks can be performed with an ohm meter. Over here I have two windings identical to the windings we're using in our transformer. One of these windings has 150 turns. Its normal resistance checks you'll have to perform on transformers quite frequently are those for an open. One of these windings has 150 checks can be performed with an ohm meter. Over here I have two windings identical to the windings we're using in our transformer. One of these windings has 150 turns. Its normal resistance is 10 ohms. This winding has 300 turns. Its normal resistance is 20 ohms. The big difference in these two windings, however, is that one of them is shorted and one of them is open. So let's use our ohm meter and see if we can tell which is which. Now remember, the PSM6 has already been set up to read resistance on the ohms times 1 scale. So let's go ahead and check the resistance of the 150 turn winding first. If we'll take a look at the meter now, we'll see that it reads infinity. Well, since the PSM6 always reads infinity for an open, this then indicates that the 150 turns winding, the one I'm now measuring, must be the open winding. We see then that an open transformer winding, primary or secondary, is indicated by a reading of infinity on an ohm meter. Now that brings us to the 300 turns windings. And since the 150 turns winding was open, then the 300 turns winding must be shorted. But let's go ahead and check it and see what indication we get. We'll take a look at the meter now. We'll see that the resistance of this winding is only 12 ohms. But we've already pointed out the normal resistance of the 300 turns winding is 20 ohms. Thus, we can conclude that some of the windings or turns of this 300 turns winding must be shorted. Well, as a matter of fact, I've already figured it out, and approximately 70 turns of this 300 turn winding are indeed shorted. Now we see then that for a shorted transformer winding, the ohm meter will indicate a resistance less than the normal resistance of the winding. Now, of course, the greater the number of turns shorted, the greater the decrease in the resistance of the winding. Now, it's also possible for one of the transformer windings to be shorted to the core of the transformer, or even for the different windings to be shorted together. However, these troubles can easily be located since the resistance between any two windings or between any winding and the core should always be infinite. Well, that brings to a conclusion this lesson on transformers. Later, when you study the various types of electronic circuits, you'll find the transformer's applications to be both varied and many. So learn them well, and until I see you again, goodbye.